Imagine you have two separate pieces of a building block set, and you want to snap them together to create a single, longer chain. In the world of organic chemistry, that's exactly what the Wurtz reaction does. It's one of the oldest and most elegant ways to take two simple carbon molecules and weld them into one. To see how this works, let's start with a molecule of methyl bromide. Picture a single carbon atom at the center, bonded to 3 hydrogens and one large bromine atom hanging off the end. This bromine atom is the key. It's like a handle, but it's a handle that's looking for an excuse to leave. Now, let's introduce our welder, a piece of metallic sodium. As we drop a sodium atom into the mix, something fascinating happens. Sodium is incredibly eager to give away its outermost electron. It spots that bromine atom and sees an opportunity. Notice what happens as the sodium approaches. It pulls the bromine atom away from the carbon, forming sodium bromide, essentially just common salt. But look at what's left behind. The carbon atom, which used to be bonded to that bromine, now has an unpaired electron. It's become what we call a free radical. It's unstable, reactive, and looking for a partner. If we have another methyl radical nearby, created in the exact same way, the two carbon atoms find each other. Watch as they collide and snap together. That single bond forming between them turns 2 molecules of methane derivative into one single molecule of ethane. We've just doubled the length of our carbon chain. But wait, why does this reaction always take place in dry ether? You'll see this specified in every textbook, and here's the reason. Sodium is famously terrified of water. If even a drop of moisture is present, the sodium will react violently with the water instead of our carbon molecules, potentially causing a small explosion. Ether acts as a safe, unreactive playground where the sodium can do its work in peace. There is, however, a clever limitation to this reaction that we should notice. Let's say instead of using 2 identical molecules, we try to mix methyl bromide and ethyl bromide. You might hope to get a clean 3-carbon chain called propane. But let's visualize the chaos in the flask. Some methyls will find methyls, some ethyls will find ethyls, and only some will find each other. You end up with a messy cocktail of different gases that are incredibly hard to separate. This is why the Wurtz synthesis is at its most beautiful when we use it to create symmetrical alkanes. It's a tool for doubling, for creating balance. So, the next time you see a long, straight carbon chain, remember that it might have started as 2 smaller pieces joined by the aggressive electron-tossing power of sodium. The Wurtz reaction teaches us a fundamental lesson in chemistry. Sometimes, to build something new and complex, you first have to pull something away.